G'day. We're going to think about approaches to the week 5 application exercise. Now there's a written solution to go with this. This is an addendum to that, I suppose. I'm going to go over the same things, but I'm going to do it just in a visual form which allows us to build up the concepts. A bit easier than reading a document that's just kind of a one and done thing. So to start off with, I'm going to pick which of the examples I want to work with today. And for personal reasons, I'll go with the Devlin's Creek example. Scouts Creek's a little bit simpler, but I love Devlin's Creek. So I'm just going to draw that to give myself, I'm going to draw a version of it, just to give myself something to operate with here on my screen. So that's DC for Devlin's Creek, and this one here is JC for Joe's Creek, and this one here is MC for Mars Creek. It's always nice to simplify things as you're working through them, any way that makes it easier for you to understand. So on this river system, we've got kind of 3 root systems. We've got the top half of Joe's Creek here. We've got Mars Creek as well. So Joe's Creek continues on, but that bottom half is not really a root system. And then we got the top half of Devlin's Creek as well. So those 3 simple river systems where some water is flowing in based on the rainfall. And then on top of that, I've got these parts of the system, which that first one's part of Joe's Creek, that second one's part of Devlin's Creek, but they've got rivers flowing into them as well as their own additional bit coming in. So I provided a few possible literal forms from last week. I'm just going to review them quickly to put them up here. I'm going to use 2 of these, I think, in my example here. I've used 5 different ones actually in the written solution, 2 of which aren't in here, one of which isn't in here. But I'm just going to stick to the ones that I put in the example. So we'll go with the 2 times one, the 2x one. We'll go with the more complicated one down the bottom, the 2.5 tilde 1 at 10 1. So what I'm going to do is show you what I mean by the literal forms for each of these. So Devlin's Creek is the top part of Devlin's Creek, that orange part, is relatively big, takes up a lot of area, probably gets a lot of rainfall, and it probably comes in relatively slowly. I'm going to go down to my solutions just so I get the same numbers I used down there. Comes in relatively slowly. So I said Devlin's Creek, every time there's 1 millimeter of rainfall, it probably leads to 8 liters per second flowing through that top half of Devlin's Creek. And I mean right here, right? So 1 millimeter equals 8 liters per second right here. And if you get 1 day of rain, let's say I'm just doing the version where you get 1 day of rain, that causes outflow for 1 day. So if I'm doing that, I'm going to represent the Devlin's Creek section as 8x, because 1 mil goes to 8 liters per second, so that's my literal form for that bit. Mars Creek takes a reasonable area in, but it's not very long, so it's going to be, when it gets to this point, 1 millimeter of rain is going to equal 4 liters per second. And Joe's Creek, quite tiny, at least at this point. So here we'll say that 1 millimeters of rain equals 1 liter per second for Joe's Creek. And the way I represent that is that one's 4x and this one's 1x. So I've got literal forms. Actually, why don't I put these in backticks so that you can see that these are the things I mean in my new language that I'm making up. Then I've got to think to myself, okay, but that's not completely defined the river system yet. I've got these green sections. So this green section down as part of Joe's Creek, it's going to have an outflow right here. Its outflow is going to be whichever water got collected along the green area, and there's some of that, which in this system I decided was 2x. But the output there is also including the output of the top section of Joe's Creek and Mars Creek. So in reality, the flow right here in my new language is 2x, the stuff that got collected just in that green section, plus the 4x plus the 1x that got combined over here. So now I've got an expression that represents this point right here. Very good. I've got the expression that represents that point there and this point here. So now I can work out what's going to come right out of there, which is the two combined, right? It is 8x plus what I just worked out there, 2x plus 4x plus 1x. Yeah. And I'm adding the extra parentheses just to help me keep track, right? And the parentheses are helping me keep track because this is the bit that came from Mars Creek and Joe's Creek combining. This is the part that came from the green bit of Joe's Creek plus the stuff above. And now this is the part that's come from the top part of Devlin's Creek combining with all of Joe's Creek. Now, ultimately, I want what comes out of here at the bottom, which is going to be that thing I just worked out plus whatever's being collected along the bottom part of Devlin's Creek, which I decided was 4x. So in the final answer was the 4x collected in the green part of Devlin's Creek plus all this stuff above, and which comes out to 8x plus 2x plus 4x plus 1x. I've done it over multiple lines just to make it fit, but it doesn't have to be like that. And again, I'm putting my parentheses in just to help me understand. So this is a single expression in my language. Things are a little bit awkward here, partly because we've only got expressions. When we were learning lots before, we learned that we could maybe write a var a equals 3, var b equals 4, var c equals a plus b. But this thing here is a statement. This thing here is a statement. This thing here is a statement. These guys, that's a single expression, that's a single expression, and that's a single expression. We haven't built up to how to parse statements yet. We've only built up how to parse expressions. So we would normally want to use variables at this point, but we don't have them. So we're having to build our expressions up by hand. I'm doing hand gestures you can't see. Build my expressions up by hand, and they get fairly complex. We're going to be quite happy once we've got variables that we can start to use. But under that version where I'm just doing with the 4x, where I go 1 mil of rain equals 4 liters per second, this here is my final expression for the Devlin's Creek system. And you and I can see how to compute that. If 1 mil of rain comes in, it will be 4 plus 8 plus 2 plus 4 plus 1, which is 12, 14, 16, 17. There'll be 17 liters per second coming out of the bottom of Devlin's Creek. But I'm not doing that computation yet. I'm just working out the expressions that describe the system. The next thing I wanted to do is to show you this in abstract syntax tree form. So I'm just going to write it out again. Let's keep switching around with my ditto pen. 4x plus 8x plus 2x plus 4x plus 1x. And I will say, for those of you who haven't realized, my handwriting's terrible, which is why I always read what I'm typing. If you're looking at something and you're like, what the heck does that say? You might have to scrub back to when I first wrote it down to listen to me say it. So this is actually an abstract syntax tree. Well, when we get this into an abstract syntax tree, this is a computation. So I want to show you that form and how we might build it up. So the most tightly bound thing is this guy here, the 4x plus 1x. So there's a plus of a 4x and a 1x. And they're related like that. And then the next most tightly bound thing is this guy here. So it's got another plus above it. And on the right-hand side of that plus is the other plus. And on the left-hand side is the 2x. And then we've got, let's move this down a little. Then we've got this part to be brought in. So that puts another plus up here. And on the left of that is the 8x. And then finally we got the last plus, which is the 4x. Okay. So we've ended up with a tree. And the tree is actually, in this case, representative of the river systems in some way, believe it or not. This part here was the top part of Mars Creek. This part here was the top part of Joe's Creek. This was the bottom part of Joe's Creek. This was the top part of Devlin's Creek. I'm just using the same colors I used last time I drew them. Top part of Devlin's Creek. And this was the bottom part of Devlin's Creek. So each of the parts of the creek that we identified have one of these literals associated with it. And the shape of this abstract syntax tree is actually somehow the shape of our river system. We've made sure that we've put the pluses in a way that that final abstract syntax tree represents the final, the original river system. Okay, so we've probably done the right thing there, because we've ended up with a syntax form that is pretty simple and matches up with the underlying system, which is what you want your languages to do. Hopefully you can agree with me that if we didn't have a proper parser and we wanted to represent this river system, we'd need some graphical format to represent it, which could be really cumbersome, difficult to work with, difficult to put into repositories, things like that. By jumping over to a text-based syntax form that underneath it has the tree anyway, we've like unlocked this world of programming. All right, now that was my version where all the water just flowed through in one day. Now I'm going to step it up and use this alternate encoding I did before. I wanted to put a bit more power into it. I wanted to say, look, it's possible that the water doesn't all flow in one day. Some of the water flows on day 1, some of the water flows on day 2, maybe even up to 10 days, right? In this case, I'm going to have ones that don't take that long, but I'm just going to redo this with those other syntactic forms, those other literals, to see if it makes any difference. At this point, because at this point we thought about literal forms last week, now we're thinking about full expressions. Expressions have binary operators, unary operators, we create trees from them. We're just going to run that same experiment with this other literal form to see what happens. Okay, so again I had Devlin's Creek, and Joe's Creek, and Mars Creek. So JC, DC, MC. I'm curious to find out if any people live on or near these river systems we're working with. We got the Canberra one, that's not local, but some of these other ones are local. If you happen to live near them, let us know. So in this case, I said the literal form isn't just a single multiplier, right? I said if 1 millimeter of rain falls, then that probably leads to a certain amount on day 1, another amount on day 2, another amount on day 3, and so on and so forth. But I used a special format for that. A special format where I said something like, in this case, I wrote 2.5 tilde 1 at 10, which was my way of representing an array where the biggest number was at index 2.5. It didn't have very much spread, just 1, and the numbers added up to 10. An example of that is, say, 1, 3, 3, 6, 7, if I go 2, yeah. An example of that is 2, 3, 3, 2, 0, 0, right? That's got the biggest number at 2.5. It's got a small spread of just 1, and the numbers all add up to 10. So I'm going to say that's, what did I choose? Let's go back down to the example solution so I can tell you which ones I chose for each river system. I've lost my original table. Okay, I don't think I've updated this yet. Okay, so I decided that Mars Creek was going to be 1 tilde 1, as in the water comes in very fast, and is a total of 4 liters per second over those however many days. I decided Joe's Creek was going to be 1.5 tilde 0. The water all comes in over just 2 days, and it's only 1 litre per second. I decided the top of Devlin's Creek was going to be 3 tilde 2 at 8, so 8 litres per second eventually, but it takes 3 days until the water really winds up. And then the bottom of Devlin's Creek, I decided was 3 tilde 2 at 4. So that's got the same shape as the top of Devlin's Creek, but it's smaller. And then the bottom of Joe's Creek was going to be 1 tilde 0 at 2. So again, the water comes in real fast, even faster than it does for Joe's Creek top. So now I've got my new literals. Am I going to do anything different when I combine them? No, I'm not. Combining them is exactly the same process, right? So if that's the flow in each of the rivers, then the flow, so that's this one's the flow right here. This one's the flow right here. So the flow just after those two combine is 1 tilde 1, whatever that literal is, at 4 plus 1.5 tilde 0 at 1. I just take the literal forms and just add them like I did before. And I can do this all the way through the system. So now down here, it's whatever it was at the start, plus this new bit that just got added, 1 tilde 0 at 2 plus, I get 1 tilde 1 at 4 plus 1.5 tilde 0 at 1. It's getting long. Now, what is it going to be right here just after these two have combined? Well, it's going to be this thing that I just described plus this thing here. I could write that out, but that's getting a bit long. And then what's it going to be right down here? It's going to be this one plus this one plus this one, which we might as well write out. So that comes out as 3 tilde 2 at 4 plus 3 tilde 2 at 8 plus 1 tilde 0 at 2 plus 1 tilde 1 at 4 plus 1.5 tilde 0 at 1. Hopefully I haven't made any mistakes. 1, 2, 3, 4, 5, feels right. So that's my final flow in this case. And if I were to do the tree again, the tree would be exactly the same shape, just with different literals in it. It would still be this tree where I've got the pluses coming down, just like I did before. And then various literals hanging off at each point. It's just that I'm hanging different literals off at each point. I'm hanging the more complicated literals off. Tilde 0 at 1, 1 tilde 1 at 4. Those tildes really start to look like 2's, don't they? So on and so forth. So the key here is that no matter what literal we've chosen to go with, the way we're building up expressions is independent to that. So that covers the basics of what I think we're going to need for this solution. But the next thing I'm going to go on to is a kind of advanced thought that I've talked about in the solution as well, so it's worth talking about here. And if you're okay with just knowing this, just stop now and you don't have to listen to the rest, because the challenge here is that the more I explain, the more I might overwhelm. You want to understand things one at a time. Once you've understood one thing, you move to the next thing. But some of the teams have been thinking this way, so I wanted to cover this idea. So plus is the obvious thing for rivers combining. But this fact that they combine, and then there's also maybe another section of river after that, means that plus doesn't quite capture everything we're trying to say. I'll draw that again. Devon's Creek. It's getting more abstract every time. Joe's Creek. Mars Creek. So at this point right here, it's very clearly Joe's Creek plus Mars Creek. And it makes no difference whether I write Joe's Creek plus Mars Creek or Mars Creek plus Joe's Creek. They both mean the same thing. They both work the same way. Those are fine. But what I wrote, let's call this section, I'm going to give this section a little name. I'm going to call it Joe's Creek bottom. So we have the top of Joe's Creek now, which is JC. We've got the bottom of Joe's Creek bottom. So when I wrote JC plus MC, totally fine. It was fine to then say MC plus JC. That makes sense. But my expression for the flow down here was JC bottom plus JC plus MC. And it's actually not okay, really, to start swapping these around into other forms. If I got rid of those parentheses, because they don't need to be there from a mathematical point of view, I might be tempted to write JC plus JC bottom plus MC, which on some of our versions will be exactly identical to the other one. But there is something in the system here I'm not capturing. What I'm not capturing is that JC bottom is downstream of JC and MC. In this one, maybe it's kind of there. That's the downstream part and that's the upstream part. So maybe the left-right ordering is showing me. But over here, I've messed that up. This is not the downstream part anymore, and this is not the upstream part. And one of the things that some teams are thinking of, which is a really good thing to think of if you choose to go down this path, all of our assumptions are saying that the water just immediately flows through everywhere. But if you decide to think, actually, water doesn't flow immediately. It takes some time for the water to get down from here. It's possible that your modeling may wish to delay upstream flows. This is an advanced type of modeling, but we might choose to put it in our language at some point. So if you were to delay upstream flows, you must include a syntax that allows you to separate upstream from downstream. And the plus probably, we can see we've kind of got it here in the plus. We could probably jam it on top of the plus where we go, the left-hand side of the plus is the downstream and the right-hand side of the plus is the upstream. But it's no longer such a perfect fit for us anymore because we're used to plus being able to get swapped around. So the suggestion I've given in my solutions, which I can see some teams heading towards, is that you have a separate operator for downstream combinations versus confluence combinations. Because what we've got here is a confluence combination, and what we've got here is a downstream combination. The JC combines downstream with the other two, whereas MC and JC just combine as a confluence. So if I chose to do that, I need a new symbol to be my downstream combination. I really like the arrow because it represents a stream. Or maybe the arrow using a tilde as the base represents a stream. And I can make them go either direction so that I can use them in any way I like, but always the head is the downstream and the tail is the upstream, right? So if I were to take that approach, I wouldn't just be able to use the plus. One thing I forgot to say back here is that if we choose to go down this path, the stuff from the Locke's textbook is everything we need for expressions. We just copy what they did for plus and move on. If we choose to go down this path though, we've just introduced a brand new operator, or probably two new operators. So we better get them into our syntax, we better get them into our scanner, and then we better include them in our parser. So it's a much more complicated, it's a slightly more complicated job for us to do, but we get extra modeling power. And just to complete the thought, I'll show you what this system would look like under that idea. It would look like JC bottom is downstream of the confluence of JC and MC. And if I did want to swap this around into a different order, I just use the opposite arrow, JC plus MC is upstream of JC bottom. Okay. This is actually a really nice position for the solution to be in. So I'm thinking ahead a little bit because I know where this is heading. You guys are unfortunately in the situation where you just got to ride this rodeo and see where it takes you, and you feel a little bit out of control not knowing where you're heading, which is one of the reasons these solutions are trying to prompt you towards the direction of things that work while still letting you and rewarding you for your creativity. So I like this. I like the plus with the combination with the up/downstream operators. I think they make a good combo, no matter which. And again, reminder, the combinations are separate to the literal forms we chose to use. So your team can choose any of those other literal forms and still choose to go with a one operator choice, just the plus by itself, or a two operator choice, a plus with a downstream, or a three operator choice, a plus and a downstream and an upstream. Entirely up to you. What I wanted to do here was just explore the way those work at the scanner/parser level. And finally, to point out that we've just done this as an exploration of expressions. We haven't actually written out grammar yet. Okay? The grammar is coming. We could do it this week. We've held it off to next week where we do the grammar and the parsing. Okay, hope that helps.